Hi guys, welcome to the post-contest discussion of the Codeforces Round 992. Okay, before moving on to the discussion, let me just introduce you all to the TLE 12.0 course, which is the flagship course of TLE Eliminators. Okay, so in this course we have four levels, and you would get everything covered from C++ basics of STL until DP, graphs, and segmentaries. Okay, so you can surely check out this course. You'll find the link in the description. Okay, so let's get started with the post-contest discussion now. Okay, so the problem A that we have is game of division. You are given an array of integers of length n and an integer k. Two players are playing a game. The first player chooses index I, then the second player chooses a different index j. Okay, the first player wins if the absolute difference between ai and aj is not divisible by k. Otherwise, the second player wins. Okay. Now the absolute, okay, the this definition of absolute value is given. So you need to determine whether it is possible for you to win if you are the first player. Okay. So the constraint of n is given till 100, the k is given till 100 only. Okay, so what we need to do is you are given nk and an array. Okay, so you are given an array and a k. Okay, so what you need to find any index. Okay, so basically what it says that it is a game. You choose an index I, and okay, sorry, you choose an index I, and the player in front of you, he would choose an index j, which says that j is not equal to I. Okay, he would choose a different index j. Okay, and then if ai minus aj mod, okay, if the absolute difference between the uh, value at index I and value at index j is divisible by k. Okay, if it is divisible by k, then it says that who wins. If it is not divisible by k, then the first player wins. Okay, so you would win if this thing is not divisible by k. Okay, so not divisible by k, it means it's not equal to 0. So if this is not equal to 0, then you say that you win. Okay, so this is what you need to make sure. Now you are the player selecting. You are the first player. Okay, so you would first select the index I. Let's say you selected this second index. Okay, then the other player can decide which j he would select. Okay, so definitely he would select such a j so that he would win. Okay, so he would select such a j so that this absolute difference become divisible by k. So you need to make sure that you select such an I so that whatever J he selects, this thing is always satisfied. Always AI minus AJ is not divisible by K. Then only you can win. Okay. If you select an index for which there exists a J so that this condition get dissatisfied or it becomes divisible by K, then that other player would choose that J and win. Okay. So it's very straightforward that you need to select such an I so that whatever j he selects, it's not divisible. Okay, and looking at the constraints, okay, you can just do a brute force. N is only up till 100. Okay, so you can just brute force through for all possible I, for each I from, okay, z, if I'm taking a zero based index. Okay, here the in the question you have to print the index also, which is one based index. Okay, so for in one based indexing, for every I from 1 to n, what you would do, just check if it is satisfied. Now how you check? Okay, this check just means that for every j you just check if ai minus aj, if at any point this things becomes divisible by k. Okay, then you say that no, you cannot do for that I. Okay, if the this thing is not satisfied for all the cases, okay, then you say that yes, this I is satisfied. Okay, and if for every I you don't get an answer, then finally you would print no. Okay, I hope the brute this was pretty straightforward, and a brute force approach was acceptable here. So I hope you would have done this problem. Okay, let me look at the doubts, sir. Okay, these question maybe we can address at the end. Okay, if you have any doubts related to the problem, then you may ask. Okay, I think everybody would have solved this A problem. It was pretty easy and straightforward brute force. Okay, so let's look at the code of this problem. Okay, so I take the input nk and the array. This input part is done. After that, I run through every possible I. Okay, I just check every possible I. Okay, my array is zero based, so I'm taking I as zero based. When I would print the answer, I would print I plus one so that it becomes one based. Okay, so that is fine. You could have taken a one based array and that was also fine. Okay, so I take zero base. So for every I from zero until less than n, okay, I just keep a variable to check if this I can satisfy my condition. So I initialize f as true and then I check for every j. Okay, for all the unique j. Okay, if I is equal to j, then that j is not valid. I put a continue. Okay, sorry. I put a continue if I is equal to j for all the other j except equal to I. If this absolute value becomes divisible by 0, then we do f equal to 0 and break. That means there exists a j for which the second player can win. Okay, then we would say that the first player cannot win with this I. Because if there is even one j for which the second player can win, then we do f equal to 0 and break. He cannot win with this I. Now, if f doesn't become 0, that means the first player can win with this I. So if f remains true even after this, that means for every j, this condition never became true. Then we can say that I is valid. So C out yes and I plus 1 is our answer. Okay, and we return here only. And if this case is never satisfied, that means for all I, this we never get a yes answer. Then at last we print a no answer. Okay. I hope this thing is clear to you. Yep, we are going with the brute force. Maybe some order of n approach may also be there, but I didn't thought of it because n was only 100, so I just implemented it fast and went to the next problem. Okay, I hope this problem is clear to you all, so we can move to the next problem now. Okay, so let's move to problem B, which is paint a strip. You have an array of zeros. Okay, you have an array of which is filled with all the zeros of length n. Okay, you can perform two types of operations on it. Choose an index I such that I belongs from 1 to n and ai is 0. Assign 1 to ai. Okay, so you can choose any index which is 0 and make it 1. That's the first type of operation. Now choose a pair of indices L and R such that L and R in the range AL is 1, AR is 1, and the sum from AL up till AR is greater than equal to this length of the range divided by 2. You can say that. And assign 1 to AI for all I from L to R. Okay. What is the minimum number of operations of first type needed to make all elements of the array equal to 1? Okay, so the first operation is just take any index whose value is 0 and make it 1. And the second operation is just take a range from L to R so that the leftmost value L and the rightmost value AR, they are 1, and the sum from AL to AR, okay, that is at least greater than equal to half the length. Okay, that means you can only have zeros and ones here, so at least half of the values are 1. Okay, that's what this condition means. So if half of the at least half of the values from the range till L to R is 1, then you can change all the values to 1, assign 1 to AI for every I. Okay, so this is the second kind of operation. Now what is the minimum number of operations of first type needed to make all elements of the array equal? That's what the problem asks, that minimum number of first type operations that are needed so that this problem can be solved. You can decide what operations you perform. Okay. And you have t test cases and an input n is given for every test case, and there's no limit on the sum of n for all test cases. Generally, it is given that sum of n for all test cases is something like that. So that means you can run an order of n loop there. But here, if you do run an order of n for every test case, it would go 1e5 into 1e4, 1e9. That would give TLE. Okay, so that's what this statement means. Okay, for each test case, print one integer, the minimum number of operations needed of first time. Okay, so you are just given an n and you need to find the minimum number of operations to make all the values in an array of length n equal to 1, minimum number of first type operations. Okay, so you can look at the example. Okay, or okay, you have an array of size 4. Let's say for n equal to 4. You have an array of size 4. Now, what's happening here is the first operation you can do is you did a first operation on this index and made it 1. Okay, that's operation 1. Okay, now after that you again did a first operation on this 0 and made it 1. Okay, that's again an operation 1 done on this index. It became 1. Now what you did, you selected this as your L, this as your R, and applied the second operation on this. Okay, so after applying the second operation, this was 1, AL was 1, AR was 1. These both conditions are satisfied. And the sum from AL to AR. Okay, this sum is equal to 2. And you can see that the length of the range R minus L plus 1 by 2, the seal of that. Okay, so this was actually 4 by 2 seal, which is 2. Okay, so this 2 is less than equal to 2. The condition was satisfied, so you were able to make all of them 1. Okay, so the condition is basically from L to R, at least half of the values should be 1. So here, out of 4, 2 values were 1. So half of the values were 1. So you were able to apply the operation, make it 1. So here operation 1 was needed. Here operation 1 was needed. Here operation 2 was needed. So number of operation 1s is 2. Okay, 2 times only you applied operation 1. So answer for this test case would be 2. Okay, so you can see for 4, the answer was 2. Okay, so I think this problem is now clear what you need to do. Okay, so how can we do this? So you are given some array. Okay, so you are given some array, and what you need to do is you need to make this array have all the ones. Okay, so how can you minimize the number of first operations? So the one thing you can notice here, whenever you need to apply a second operation. Okay, so to make all of them one, what you would do, the last operation that you would perform would be like for the complete array, if you can perform a second operation, then all of them would become one. Okay, that probably could be your last operation. Now how would you be able to do that? If you have a 1 here and a 1 here, then only you would be able to do that, and at least half of the values should already become 1. Now initially you start with all the zeros. Okay, all of the values are zeros. Now how do you make them 1? So to make whenever you apply an operation of second type, you are basically, if you have 5 ones, let's say you have 5 ones, then at max you would be able to make 5 to 10. You cannot jump more than that, because for the condition is that you should have, like, whenever you apply a second operation for the range from L to R, you should have at least half of the values already 1. Then if you have exactly half of the values already 1, then the count of ones would just get doubled if you apply the second operation. So one thing we can notice that to minimize first operation, you are going to use more and more second operations, utilize them in such a way so that you are able to get more ones. Okay, so with operation 2 we can say that whenever we apply an operation 2, okay, we can make the count of ones, okay, c1 double using operation 2, but not more than double. Okay, so we cannot, so one conclusion is we cannot C1 would never become more than 2 times C1, like after applying the operations. Okay, so it would be always like C1 dash would always be less than equal to 2 times C1. This we can say that if you have C1 initially, then after the second operation, it would remain less than equal to 2 times C1. You cannot make it more than 2 times C1. So initially when you have all the zeros, you cannot apply a second operation first of all here. Okay, so you should have at least a one. So you would have to apply one of the operation one at least. Okay, so at least one time you would have to apply operation one. That's also another conclusion that you can get. Now, also the thing required for the second operation was AL should be 1, AR should be 1. Okay, this condition was also required. So you can notice that like if you are taking L and R both the same, then there is no use of second operation. So if you want to use the second operation to get some benefit, AL won't be equal to AR. So that means at least two values should be 1. Okay, so that's another conclusion, that in order to use the second operation, you would have to use at least 2 times first operation. Okay, so now let's say you made this one and this one. Okay, then you try to use the second operation on this. Now you can make all of them 1 if after this you have a length of 4 only. If n is equal to 4, if n is greater than 4, then you cannot use the second operation directly. Okay, now what you would do? So if you have 1, then at max, in order to use the second operation, you would, so if you have a bigger array, how would you optimally fill it? After this one, you would probably fill this fourth value as 1, so that you can apply a second operation and make these two 1. Okay, without any extra cost. So you would assume that the first operation is only taking the cost. Okay, that's what you need to minimize. So second operation is free, you can apply it any number of time. So if you apply first operation here and a second let's say if the second first operation is applied here, okay, then using a second operation you can just increase the count of 1 by 1. Okay, just this one would get filled. But if this first operation is applied instead of there, if you apply it here, then you can make both of them 1 using a second operation. But if you take it here, let's say, then you cannot apply a second operation here, because these there are 3 zeros and 2 ones only. So out of 5 by 2 seal is 3, so you should have at least 3 ones here. Okay, but there are only 2 ones. So the most optimal place to apply the first operation, okay, if you have applied first on the leftmost, then it is on the fourth value. So after these two operations, apply a second operation and make all of them 1. Okay, so number of operations of first type, you applied here 1. Okay, so I'll say that here you applied a first operation, and then here you applied a first operation, and then in these here you applied a second operation to make these as 1. Okay, then where would you apply the first operation? Okay, after this, now all these 4 are 1. Okay, then maybe you can apply a first operation here and then a second operation on this to make this also 1. Okay, so this is one possibility. You would only get one extra 1 by applying the second operation after this. Okay, so instead if you apply the first operation here, then you can use a second operation on this and make these zeros into 1. That's another possibility. Okay, or if you take this one here, okay, if you apply this first operation here, then in this array also, if you see 1 2 3 4 5 ones are there and only 3 zeros are there, so again you can make them as 1 1 using second operation. If you take it there, then here also you can, there are 5 ones and 4 zeros. Similar way, if you take it here also, still in this array you have 5 ones and 5 zeros. So here also you can apply the operation. But once you take this one here, then in this array you cannot apply an operation, because there are 11 values in total. Out of them only 5 are 1. Okay, so the condition for second operation won't be satisfied, so here you cannot apply. So you got the point that after this, at least you would have to make this place 1 Okay, at least one more operation on this would be required in order to make all of them 1. Okay, so if you look at the indexing, this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so first you applied the first operation on 1 and then on 4. So with second operation you made all of them 1. Then you applied the next first operation on 10, and then using the second operation you made all of these 1. Okay, after that, now only one, if n is equal to 11, if we are supposing, then only one place is left. So you will you will have to apply the first operation to make it 1. Okay, so here you cannot make something to here as 1 without the first operation. Like if this is already 0, if you try to apply the second operation here, maybe, okay, that condition is satisfied that you have more number of ones than half the length. But here this AR is not 1. Okay, so AR equal to 1, this condition won't be satisfied. So in order to make this 0 as 1, you would have to, if it is on the corner, you would have to make it 1 by yourself only, by using the first operation only. Okay, so here also one operation of first would be required. So in total, 1, 2, 3, 4 operations were required. Let's say here n was 12. Okay, so if n was 12 here, you have another index which is 0. So here what you could have done, you could have applied the first operation here. Okay, and then using the second operation, you could have made this as 1. Okay. So again, 1, 2, 3, 4 in 4 you were able to do. Okay. With 13 also, you could apply the first operation here and using the second operation, make them 1. Okay. So up till where, using only one more first operation, you can make all of them 1. Okay. Same way, if you analyze this thing. Okay. So then what you would get is, okay, let's say, so 13, 14, 15, 16, 17, 18, 19. Okay, so if you like, if you look at here, if you have applied the third first operation on 10, after that you can make this one and apply the second operation here, make them 1. You can make this one, apply second operation, make it here, until where you would be able to apply a first operation. So in 20, if you make it 1, then from 10 to 20, like in from 0 to 20, there would be these 10 ones and 1, so 11 ones would be there. Okay, even if you apply on 22, okay, so even if you apply the first operation on 22, still you can see that here from 1 to 22, in this array you can use a second operation, because out of 22 values, 10 values are already 1, and this one 11 values are already 1 out of 22 values, so half of them are already 1. So you can use a first operation here, and using second operation make all of them 1. Okay, so if the value of n is from 11 till 22, your answer would be 4. That you can notice. Okay, if n is equal to 10, then in 3 operations you can do. But after n is greater than 10, you would have to use a fourth operation. So from 11 till 22, you can say your answer would be 4. From 5 to 10, your answer would be 3. Okay. So you can say for n equal to 1, your answer would be 1. For 2 to 4, okay, if n is equal to 2, 3 or 4, your answer would be 2. If it is 5 up till 10, your answer would be 3. 11 up till 22, your answer would be 4. After 22, your answer would be now 5. Okay. So now, how am I getting these boundary points? After 1, I got 4. After 4, I got 10. After 10, I got 22. Can you notice some pattern? Okay, yes, it is 2x plus 2. Okay, so after 1, 2 into 1 plus 2 is 4. So you got 4. Now 2 into 4 plus 2 is 10. So you got 10 next. Okay, 10 into 2 plus 2 is 22. Okay, so you got 22 next. Okay, so if you do 2x plus 2, if x equal to 2x plus 2, if you are doing this, then you will get the next values until then. Like y 2x plus 22. Okay, not it's not about just noticing the pattern. It's also about noticing that, like, if till 10 you were able to make all of them 1, okay, then if you take the x value and you want this to be equal to like, so that I can apply the second operation, then what it would be. So for 10, if you make it 20, then from here you already have 10 values, and wherever you place this another first operation, you would get 11 values. Okay, so if you have x values already 1, then after using another operation you would have x plus 1 values already 1, and you can see that using the second operation at max you can make it double. So you are making x plus 1 double. That's why you got 2x plus 2. Okay, I hope this logic is also clear. So this way we can analyze that for 1 your answer would be 1. Now 1 into 2 plus 2 is 4. Okay, so from 2 up till 4 your answer would be 2. Now next is 4 into 2 plus 2, which is 10. So from 5 up till 10 your answer would be 3. Okay, next is 22. So from 11 up till 22 your answer would be 4. Okay, so this way we can move, and initially only, now you can see the constraints of the problem, that n was up till n was up till where's the, n is up till 10 to the power 5, and for, if for every test case you are moving and analyzing, then that would take an order of n time. Okay, for every test case that would go give you TLE, but you need to answer for these n from 1 till 1e5. So before the test cases only you can pre-compute the answers. Okay, so as I said, using this pattern you can just pre-compute your answer from 1 up till 10 to the power 5 for all the values. For all these values you can just pre-compute your answer. Okay, so for 1 my answer would be 1, for 2 my answer would be 2, for 3 my answer would be 2, for 4 also my answer would be 2. Okay, after that move to 10. Okay, so from 5 till 10 assign 3 to your answer array. Now next is 22, so from 11 till 22 assign 4 to your answer array. Okay, so you can just pre-compute your answer array, and then for every test case in order of 1 only you can just answer from that answer array. Okay, I hope this logic is also clear to you. Okay, is there any doubt in this approach or the logic? Okay, okay, it's clear to you all. So we can look at the code now, the implementation of this. So I just initialize my answer array of size 1e5 plus 5. Okay, so plus 5 is just extra. You can initialize it 1e5 plus 1 also, so it would have indexes up till 1e5. Okay, so this is my answer array. Now in the main function, before going to the test case only, I am doing the pre-computation part. Okay, so in the pre-computation part, what I am doing, I'm initializing that answer for index 1 is 1. Okay, so for n equal to 1 my answer would be now 1. Okay, so now what I did is I just initialize this j equal to 2. Okay, so through j I would store my answers. Okay, this would be the index of my answer array, and then I'm running a loop from 2 to 1e5. Okay, so x is what is the values. Okay, so it starts with 1. Now I would update x as 2x plus 2. Okay, so in every iteration I'm updating x as 2x plus 2. So x is initially 1. Now it becomes 2 times 1 plus 2, which is 4. Now when it becomes 4, I'll say for 1 my answer is 1. Now from 2 up till, okay, j is initialized with 2, so from 2 up till this x. Okay, so while j is less than equal to x, I would update my answer as I. Okay, so I is, so okay, initially my answer was 1, now I is 2, so that answer would be updated to 2 for every index from 2 up till 4. Okay, now again, if x becomes greater than 1 5, I would break. Now next iteration, 4 into 2 plus 2, x becomes 10. Okay, now j is already at 4. Now until j is less than equal to x, my answer is updated to 3. Now in next iteration I'm going to 3. Okay, so this way I hope this code is clear, that I'm just updating my answer array. Okay, until j is less than equal to x, I just update it. Okay, and when this x becomes greater than 25, I break out. Okay, this loop is running till I less than 25, but this has no sense. It's actually until you can actually write x is less than equal to 25. That would be a better condition. So I would not have to write this break here. I think yeah, this code would also be fine and this would be better. Okay, so until x is less than equal to, or j is less than equal to 25. Okay, j is, sorry, not x, j. Okay, j is the index which I'm filling. Okay, so until j is less than equal to 25, I am just filling this up. Okay, so that should be the condition for my for loop. Okay, so I hope this pre-computation part is clear to you. Now for I take the test cases, and then for every test case I take an input n and just print answer of n. Okay, so in order of 1 I'm handling every test case, and this pre-computation part is taking order of 1e5. Okay, so this is taking an order of 1e5. Okay, because inside this while loop also, every time I update j, I do j plus plus, and j is going up till 1e5. So at max, I'll have j times this would be updated. So overall, this loop is only running order of 1e5 times. Okay, so this loop is running 1e5 times pre-computation, and this test cases are 1e4. Okay, so for every test case, this thing is just, you can say that, order of 1. Okay, so I can write my overall time complexity as order of 1e5 plus every test case. Okay, so test cases are 1e4 only. So it's actually 1e5 plus 1e4, which is well accepted. Okay, so I hope this problem is clear to you. No, is there any doubt on this? Okay, I think it's clear. Okay. Okay, so I think we can move to the next problem. Yeah. Okay, so problem C, we have that ordered permutations. Consider a permutation of integers from 1 to n. We can introduce the following sum to it. S, or the sum of the this S of P is what? This is for like for L and R in the range from 1 to n. It just means that we are iterating through every subarray, and this min is the minimum of that subarray. Okay, so for every L and R, okay, that means we are iterating through all the subarrays and taking the minimum of that subarray, adding that to our answer. Okay, so this sum is the sum of min of all the possible subarrays. That's what this means. Okay. Let us consider all permutations of length n with maximum possible value of SP. Okay, now we would consider all the permutations of length n, and for every permutation of length n, we calculate this sum. Okay, and among them, whichever is the maximum value of the sum, for whichever permutation we get the maximum value. Okay, so if we consider those permutations where we get the maximum value, the kth of them in the lexicographically order, that's what you need to report. Okay. Okay, so I hope if the problem is not clear, let's look at this example to understand what this problem says is, let's say you need to find, okay, so for the problem you're given n and k. Okay, let's say you are given 3 and 2. So if you are given 3 and 2, that means n is equal to 3. So for n equal to 3, these are all the permutations that exist for n equal to 3. Okay, so for n equal to 3, all the permutations that exist are these. Okay, so there are 6 permutations for n equal to 3. These are all the permutations. Okay, let's look at the first permutation 1, 2, 3. For this, what would be the value of S of P? Okay, so for P equal to 1, 2, 3, what would be S of P? Now you would consider all the subarrays. Okay, initially for the subarray starting with the first index. So for this subarray, your minimum is 1. Okay, now for this subarray, your minimum is among 1 and 2, it is again 1. Now for this subarray, just 1 itself, it is again 1. Now if you look at this subarray, Among 2 and 3, the minimum is 2. Now, if you look at just this subarray, just okay, or just this subarray, just 2. If you look at just 2, again, its sum is 2, minimum is 2. And if you look at just this subarray, only 3, then its minimum is 3. Okay, so all the 6 subarrays are considered, this, okay, then this, and this. Okay, for all the 6 subarrays, these were the values of minimum of the subarray. Okay, when you add it up, you get 10. Okay, so for this, your S of P was 10. Same way you can compute for 1, 3, 2. Okay, for this minimum is 1. This minimum is also 1. This minimum is 1. Okay, this minimum is 2. This minimum is 3. And this minimum is 2. Okay, so this sum would is also 10. Okay, so I hope you know how to compute this. Okay, so for this also, if you try to compute, you will get 9. For this, you will get 10. For this, you will get 9. For this, you will get 10. Okay. Now, for every permutation, once you have computed, what is the maximum value? The maximum value is 10 here. Okay, so which all permutation are giving the maximum value? Okay, so among this, the maximum was 10. Which all permutations are giving 10? This is giving me 10. This is giving me 10. This is not giving me 10. Now, this is giving me 10. This is not giving me 10. And this is giving me 10. Okay, so among these 4 permutations, if you arrange them in lexicographic order, now these were already arranged in lexicographic order. What does lexicographic order means? That basically the first is compared with first. So if the first is same, then you compare the second. Okay, so like although starting with 1 would be before, likewise, I hope you know what lexicographic order is. So in lexicographic order, this would be first, this would be second, okay, this would be third, and this would be fourth. Okay, so in lexicographic order, this would be ordering. Now, here in the first test case, k is given as 2. Okay, so when k is given as 2, you would answer the second permutation. So this 1, 3, 2. Okay, 1, 3, 2 is answered here. Now, in the next test case, for same n equal to 3, you are given k equal to 3. So for k equal to 3, you would answer the third permutation, which is 2, 3, 1. So you answered 2, 3, 1. Okay. If k was given like for this 3 only, so for n equal to 3, let's say if k was given as 5. Okay, so then what you would say, you only have 4 permutations which are valid here. So 5 permutations are not there which are giving me maximum. So for this, you would answer a -1. Okay, so this is what the problem statement is. I hope the problem is clear to you if it wasn't clear. Okay, now how would you solve this problem? Okay, so if you try the brute force approach, that just go to all the permutations and for them compute the sum. So what would be the complexity of that brute force approach? Okay, so if you just try the brute approach, what it would be? So go to for each permutation, just go to each permutation and for them compute the sum. Okay, so for going, there are n factorial number of permutation, and for calculating the sum, you would go to all possible subarrays which are n square. So this would be your time complexity, and I hope you know that this would not be accepted. Okay, the constraints of the problem is n is 2 into 10 to the power 5. So for this, and leave n factorial aside, even this n square you cannot do. Okay, so this n square also, if something of order of n square you are trying to write, that would also not get accepted. Okay, so you need to calculate this thing optimally. Okay. 2 to the power n, not 2 to the power n, it would be n factorial if you are going to all the possible permutations, because there are n factorial permutations. Okay, so now how do we do it optimally? That's the main thing. Okay, now you cannot do n square. So even calculating the sum for any one particular permutation is not possible here. So you need to find the max permutation having maximum sum. So the kth permutation having maximum sum. Okay, so if you analyze the sum, how first thing is you need to maximize the sum. Okay, okay, let's leave aside finding the kth permutation. Let's, even if you want to find any one permutation where the sum would be maximum, which permutation would that be? If you try to think, Okay, so whenever you have an array, okay, let's say you have an array of size 5. Okay, let's say for n equal to 5 we are analyzing. You have a permutation of size 5. 1, 2, 3, 4, 5. Okay, now in this, whatever value you have here, okay, so how many subarrays would be there for this? Okay, so like you would have, what all subarrays you would have? You would have this subarray. Okay, so all the subarrays starting from here. Okay, so these 5 subarrays would start from 1. Okay, then all the subarrays starting from 2. So you would take this, this and this. Okay, then all subarrays starting with 3, you would take this and then you would take this, this and then you would take this. Okay, I hope it's clear what all subarrays would exist. Now, for this, let's suppose you have one somewhere here. Okay, or you have one somewhere here. Okay, now whichever subarray contains 1, for that the value that you would add would be 1. The minimum would be 1, because if you have a permutation from 1 to n, okay, and in any subarray there is a 1, then 1 would be the minimum. There is nothing less than 1 here. Okay, so wherever this 1 goes, for that part, for that subarray, you would add +1 to your answer, because the minimum of that subarray would be 1 only. That's the first observation. I hope that is clear now. Now, if you have this one, okay, so in what all out of 15 values? Okay, so for this, if you take the sum of the permutation, what would be like, how many subarrays for this, for n equal to 5, how many subarrays exist? Okay, so there would be n into n plus 1 by 2 subarrays in total. If you see, there is 5, like 1, 2, 3, 4, 5. Okay, 5 subarrays starting with 1, 4 subarrays starting with 2, 3 subarrays starting with 3, 2 subarrays starting with 4, 1 subarray starting with 5. So total 5, 4, 3, 1. Okay, so which is 5 into 6 by 2, n into n plus 1 by 2. Okay, so you have n into n plus 1 by 2 subarrays. For 5, this is equal to 5 into 6 by 2, which is 15. Okay, so S of P would have like 15 values which you would sum up. Okay, so among those 15 values, let's say you have in this permutation, if you have 1 here, so among these 15 values, how many values become 1? So in whichever subarray you have this 1, that value would become 1. And for whichever array you don't have 1, that value would be greater than 1. That is for sure. Now, let's look for every index, for every position, what is the weightage of that position, or you can say in how many subarrays that position would come. Okay, so if you have this one here, then you can say this one is coming in this and this, a total of 5 subarrays. In total of 5 subarrays, among these 15, in 5 subarrays this one is coming, and all the remaining 10 subarrays this one is not coming, that you can say. Now, if this one was here, let's say, instead of here, if it was where, then in how many subarrays it would come? In this subarray it would come. Okay, and then in this subarray alone it would come, then this. Okay, so 1, 2, 3, 4, and this is 5. Okay, and one more would, okay, and then for this also it would come, for this also it would come, for this also it would come, for all of them. Okay, so all the subarrays starting from here, except starting here and ending here only. Okay, so this, so 4 here, then starting from here, this and this, so 4 there also. So I think it would be 8. Okay, so in 8 subarrays this is coming. Now, how can you calculate in general for any ith index? For any ith index, you can say for which all subarrays that would be coming. It would be, so for any subarrays for which this index is coming, it means it should start before it and end after this. Okay, so your L should be before this, R should be after this. Okay, so for any I, if you are at ith index, so all the subarrays containing ith index would be how many values are to the left of I. Okay, so so how many values left of I, so it would be I values, and how many values to the right of I, that would be n minus I minus 1, I plus 1 values. These many values are right of I including I. So the product of this you can say. Okay, so uh, these many subarrays would exist which would contain I into n minus I plus 1. Okay, so like for 2 you can say it's 2 into 4. Okay, so here you can say 2 into 4 subarrays. Okay, starting from this all these, and starting from this all this. Okay, so in left we have two options, for R we have four options. For here it would be, for L we have three options, for R we have three options again, so it would be 3 into 3. For this position we have, in L we have four options, in R we have two options. Okay, so 4 into 2 here, and here 5 into 1. Okay, so I hope what here I am getting, these are in how many sum this index is coming. Okay, so if you are looking for 1, if 1 is coming here, that means out of these 15 values, 9 values would have 1. Okay, and if 1 is coming here, that means out of 15 values 8 would have 1. Okay, so if you write this, this is 5, this is 8, this is 9, this is 8 again, this is 5 again. So among these, this middle one would be maximum. So this way you can understand that always the middle value has some more weightage in subarrays. Okay, so what you would want in order to maximize this sum, you would want that one should be placed at such a position which has very less weightage, so that less of the values would become 1. So you try to place it on the corners only. Okay, so if you place it in the first place, only 5 values out of the 15 would become 1. Rest of the 10 values would be greater than 1. So, but if you are placing your 1 here, that means 8 values would have 1 here and rest would have greater than 1. So that would obviously increase your sum. So you would always place the 1 either to the leftmost side or to the rightmost side. Otherwise you would have get something greater. Okay, you could have made it smaller. So that's the first logic, the first intuition that you get. Now let's say you have two options for placing the 1. You can place it here also or here also. Let's say you placed it here. Now for the remaining array, what should be the position of 2? Now let's say you place your 2 here. Okay, so this 2 has weightage 8, but if you look, okay, like, or let's say you place your 2 here, this has weightage 8. Okay, but and this 2, if you put your 2 here, then this has weightage 5 only. But if you look, even though it has weightage 8, but out of them there would be some subarrays for which you are considering this also. So for them, the value would be 1. For all the subarrays which doesn't contain 1, for them your value would be 2. Okay, 2 would be the minimum. So if you are considering this index where you have already placed 1, then all subarrays containing this index would be 1. Okay, so let's ignore all of them. So if you ignore all the subarrays containing this 1, so this are ignored. That means you are just considering all the subarrays in this. Okay, that means your question is like reduced to n equal to 4. For this n equal to 4, you have to do the filling from 2 to 5. That's what your question is currently reduced to, because all the subarrays containing this index has become 1. So you have, for 4 values, for n equal to 4, the value of n into n plus 1 by 2, this would be 10. Okay, so you have, so as you can see, Out of 15 values, 5 values have already become 1, and 15 minus 5 is 10. So 10 values are remaining. These are the 10 values. That is for n equal to 4, the all possible subarrays. Now, among these, where would you place the 2? Now, for this subarray, 2 is your minimum. So, where you need to place the 2 at some place which minimizes the number of places where you have 2, because for all the other places you would have greater than 2. So again, 2 would be placed either for this subarray, the leftmost is this index and the rightmost is this index. So for this subarray, 2 would be placed either here or here. Now, if you place this 2 here, you are remaining with this basically array for n equal to 3. You would place 3 either here or here. Okay. Or if you would have placed your 2 here, okay, then you would have you would have been left with this array with size n equal to 3. For this, you would place your 3 either here or here. Okay. So now I hope you can understand how to construct the permutation having maximum sum. Okay. So always start. Okay. So whatever you want to construct, always fill the one either here or here, either the first place or the last place. If you fill it at the first place, then in the remaining array, whichever is the leftmost and rightmost, those are the two options for placing 2. Okay, let's say you pick your place your 2 here, then your remaining array is this. Now in this, either you place your 3 here or there. Okay, if you place your 3 here, then you would be left with this. Okay, then if you place your 4 here, you would be left with this. I hope this logic is now clear. So always you would have two options, either the leftmost or the rightmost. Okay, and then next again you have two options. Okay, so this way I hope you can now understand how many permutations having maximum sum would exist. Yeah, someone is saying we can simply fill in descending order. Yeah, we can do that. That just means we are always filling in the rightmost part. Okay, so if you have, you can always fill in the rightmost part, it would become 1, and then in remaining you fill in the rightmost, it would become 3. Then you pick rightmost 3, 4, 5. Okay, so this is one option, or you can fill in the ascending order. So 1 here, so you are always filling in the leftmost. So if you are always filling in the leftmost in the remaining array, it would become ascending order. But you can also do a mix of them also, where at some point you filled in the first, then at the last you filled. Okay, then again first, then again first, and then last. Okay, you can do a mix up of them. For this also you would get maximum sum. Okay, so I hope how many such permutations having maximum sum would exist. How do you calculate that? If you try to find out. So at every point, okay, so for 1 we had two options, the first and the last. After 1 is filled, for 2 we again have two options, the first and last. Okay, so for 1 we had two options, for 2 also we would have two options, for 3 also we would have two options, and for n also we would have two options. So you can see the total number of possibilities would be 2 into 2 into 2 n times, which is 2 to the power n. Okay, so like not n times, for n minus 1 you would have two options. Okay, when you are moving to the nth index, you would have only one place remaining, so that would have to be filled there only. So from 1 till n minus 1 we would have 2 to 2 options. Okay, so n minus 1 times, and then you have one option only. Okay, so it would be 2 to the power n minus 1. A total of 2 to the power n minus 1 permutations would exist having maximum sum. So you can verify it here. For n equal to 3, we saw that a total of 1, 2, 3 and 4. Okay, 4 permutations were existing. So for n equal to 3, what is 2 to the power n minus 1? It is 2 to the power 2, which is 4. Okay, so this way we can verify that for n equal to 3, 2 to the power n minus 1, that is 4 permutations, have the maximum sum. Okay, so I hope this is clear to you. So now the first thing is the value of -1. So if k is greater than 2 to the power n minus 1, then you would just print -1. That you cannot obtain a permutation, that the kth permutation doesn't exist. You only have 2 to the power n minus 1 permutations only having maximum sum. Okay, so this is the -1 case. Like here you can see in the third test case we had -1. For n equal to 4, for n equal to 4 you can see, for n equal to 4, 2 to the power n minus 1 would be 2 to the power 3, which is 8. But k is given as 11. So 11 is definitely greater than 8, which is 2 to the power n minus 1. So you printed a -1 here. You printed a -1 here. In the last second test case for n equal to 6, it's 2 to the power 5, which is 32. 39 is greater than 32. You print a -1. Okay, so I hope this -1 case is clear to you. Now, for any other case, okay. Okay, is this clear? Someone is was telling to repeat this 2 to the power n minus 1 thing. If it is not clear, then please tell which part is not clear. Like what I explained, or if it is now clear, then you can write. Okay, so what I explained was, for one, you have two options, either leftmost or rightmost, two options. Once one is placed, you would place two. For that, again, you would have two options, leftmost, rightmost. So two options there. For three, again, two options. That way, up till n minus one, you would have two options. Now, once you have placed four values, let's say, then only one place is remaining. So there are no options. That nth value has to go there only. So you have only one option. So for you have would have n minus 1 times 2 into 1. So 2 to the power n minus 1. Yeah, this is somewhat combinatorics problem only. Okay, so I think this -1 case is clear now. For a general case, how do you compute? So among these 2 to the power n minus 1 permutations, okay, so like this, there would be 2 to the power n minus 1 permutations, which would give you the maximum sum, which would be lexicographically kth, that you need to determine. Okay, so let's see for n equal to 3. What was the case? For n equal to 3, what all? So this was one way to analyze that. Take all the permutations, calculate their sum, and you would have 6 permutations, calculate their sum. Now, we know this brute force would not work. And then we simplified the problem by saying that for the maximum permutation, it would be always like this. Place it at the first place or the last place. So our permutation, so what all possible cases are there? Either we would place one here, or we would place one here. Okay, then if we do it like this, then for this also two cases, either we would place two here or two here. Okay, so either if we place two here, then this case, or if we place two there, then this case. Again, for this also two cases, either we can place two here or two here. So if 2 is placed here, it's this case, and if 2 is placed here, it's this case. Now, for this, there is only one place remaining. We would have to place 3 there only. Okay, so 3 would have to be placed there only. It becomes 1, 2, 3. It becomes 1, 3, 2. This becomes 2, 3, 1. And this becomes 3, 2, 1. Now, you can look at this, what all permutations you had. 1, 2, 3, 1, 3, 2. Okay, 1, 2, 3, 1, 3, 2. Then 2, 3, 1, 3, 2, 1. Okay, 2, 3, 1, 3, 2, 1. These four permutations were only there. Okay, that's how you calculate those possible maximum permutations. Now, how you arrange them in lexicographic order? So for lexicographic order, you know that whichever array is starting with 1, that would come first. Okay, so in this first, okay, so initially you were given this array which was initially empty. Now you have made it into two cases. Either you place your 1 here or here. So when you place it here, it becomes this, it becomes this. Now in lexicographic order, through this side whichever permutations you obtained. Now, if you place your 1 here, that would always be less than if you place your 1 here. So, you know, when you are placing your 1 here, all the permutations after that you would obtain, they would be lexicographically smaller than all the permutations you obtain from this. Okay. And then again, when you place your 2 here, so if you place your 2 at the start, that would be less than when you place your 2 at the end. So if in this, like in this tree kind of thing, in this, like you can say this is a recursion tree where you are placing it first or last, or like the 2 to the power n uh, values that you would obtain. Okay, it's growing exponentially. So in this you can analyze if you are first placing that when you are placing at the first, and after that you are placing when you are placing to the right, then the final that you would obtain, that would be in lexicographic order. Now in this, if you want to find the kth value, okay, let's say k is 3. If you want to find the kth value, now calculating this whole thing would take 2 to the power n complexity. Now you cannot do it in 2 to the power n complexity. You need to do it in something like order of n, or greater than n, but not even n square, and 2 to the power n is definitely not accepted. So what you can do is, in this only, based on the value of k, you can decide whether you would go this side or that side. Okay. So here if k is given you as 3, okay, then if you are placing your 1 here, then for this case, how many values you would have in the end? There are 2 empty places, so number of ways to fill would be 2 to the power 2 minus 1, 1. So 2 ways would be there. So if k is less than equal to 2, you would go this side, that it means you would place your 1 here. And if k is greater than 2, you would go this side, you would place your 1 here. So based on looking at the value of k, you can decide whether you want to go this side or that side. Now if k was 3, so looking at the value of 3, you decided you would go this side, that means you would place your 1 here. Okay. Now in this, what you are searching for? In this you are searching for, like you can say this was n equal to 3 case. Now this 1 is already filled. This is effectively n equal to 2 case for this thing. But for this thing, if you're considering n equal to 2 case, then 2 to the power 1 ways are there. So out of that, if you won't compare this k with that. But what is your effective k now? Okay, so here you are searching for the third element. Now here which element are you searching? Already 2 elements you have bypassed. So now you are searching for the first element in this. That's what you are searching here. So you would, like in your recursion you can write that when you are moving this side, you reduce your k by 2 to the power n minus 1. Okay, like, or 2 to the power n minus 2 it would be. Okay, so here you two values were already considered, so you reduce your k by 2. Here you are for n equal to 2, you are searching for k equal to 1. Okay, instead of k equal to 3, because two values you have already skipped. So now here you are searching for the first value, not the third value. Okay, if k was 4, let's suppose. Okay, then here you would see that if you place your 1 to the left, then this would have 2 to the power 1 cases. Okay, so which is 2. Now since this 4 is greater than 2, you would move right side, not left side. Okay, so you would move this side, you would place your 1 this way, but you would reduce your k by 2. From 4, your k would now become 2. Okay, so this way you can move. Now if you need to find the second value, so if you move to the left, you would have possibilities of 2 to the power 0, which is 1. Okay, so you have one possibility to the left. Now k is greater than 1. Since this 2 is greater than 1, you move to the right. If it was k equal to 1, okay, that means for k equal to 3, if you were analyzing, you would get k equal to 1. then you would move left side and obtain this. And now for equal k equal to 2 you are analyzing. So this condition of k less than equal to 2 to the power 0 in this case is not satisfied. So you move to the right, and here you got this permutation. So in this way, if you move based on value of k, if you are deciding, then at max you how many times you would move. Okay, so the depth of this recursion tree, which is order of n only. So n equal to 3, n equal to 2, n equal to 1, n equal to 0. So this way in order of n only you are able to compute. Okay, so what I'm telling is you would move in a recursion where effectively if you're where you would say that if you're calculating f of n comma r, okay, then n comma k. Okay, so if you're calculating for n comma k, then that's effectively for n minus 2. Based on the value of k, you would place the value either in the first index or in the last index. And then for the remaining array, it's equivalent to in the remaining array, that is for n equal to 2. If you are computing for k equal to, if you are moving to the left, k would remain k. If you are moving to the right, k would reduce by 2 to the power n minus 2 actually. Like for n equal to 3, it got reduced by 2, which is 2 to the power 3 minus 2, 2 to the power 1. Okay. So this way you can write f of n. From f of n, you would move to f of n minus 1, comma k, or f of n minus 1, comma k minus 2 to the power n minus 2. So either this or this, that would be based on the value of k. Okay. So if k is less, like, okay, so it would be this case if k is greater than 2 to the power n minus 1. Okay, sorry, 2 to the power n minus 2. If k is greater than 2 to the power n minus 2, you would move to this case, else you would move to this case. Okay, so this would be your recursion. And again, you cannot write it as n because you also need to specify where you are putting the value. So I'll take L and R to represent that. Initially, I'm calculating for 0 to n minus 1. So L and R represents the range for which I'm talking about. Okay, so when I'm moving ahead, I'm reducing my range. Okay, I'm reducing my range. That I'll denote with L and R. Okay, so I hope the implementation is clear that we would make a function having L, R, and K, and the current value which okay, so I would start with 1. Initially I'm putting the value 1, then I would be putting the value 2, then put the value 3. Okay, so to that I can keep a variable I, and in that we check if k is, now here what is n, the length n is r minus l plus 1. This is what n is. So n minus 2 is actually r minus l minus 1. Okay, so we would check if k is greater than 2 to the power r minus l minus 1. Then we go to f of, okay, so what we do in this case, if k is greater, then we place the I at the end, okay, at index r. So we say that a of r is equal to I, we put that, and we call the recursive function again from L till r minus 1. Okay, r is done, then L till r minus 1 is the remaining range. For that we call the recursive function, and this would be for k minus 2 to the power r minus l minus 1, and this I would become plus 1. Okay, so this would be for this case, and you can write for the else case. You would call, you would say your al is become I. Okay, in the left side you would place the 1. Okay, in the left side you would place the 1 or the I, and then you will call the recursive function again for l plus 1 up till r. Okay, and k would remain k because you are moving to the left, and for I plus 1. Okay, I hope this recursive function is clear to you. In this way, the base case of the recursion would be when you have only one value. Okay, so base case of the recursion would be if L is equal to R, then you just place that at AL, you would place the I and return out. Okay, so this would be the base case. I hope it is clear. Now through this recursion, we would be able to compute our answer in order of n. Okay, is it clear to you? So I think we can look at the code now. I have written the pseudocode. The code would be somewhat the same. So here we create this recursive function. In this we take an I, L to R for the range which is my current array which we have to fill. K is the K that is given in the question, and we are passing by reference our answer array where we would put the values and create our answer. Okay, so if L is equal to R, we put the base case, the answer of L becomes I, and we return. Okay, this is the base case when you have only one index to fill, so your range L and R are the same. So that index would be filled with I and we return out. That's base case is covered. Otherwise, this size would be R minus L minus 1. Okay, so we have to take 2 to the power R minus L minus 1. So that we would put in a variable size, and we check if 2 to the power size is less than K. Okay, now this condition. Okay, so we were checking if 2 to the power size is less than K. Okay, or K is greater than 2 to the power 5. This was the condition we were checking. Then we would move to the right. Okay, so if 2 to the power, if K is greater than 2 to the power size, if K is greater than 2 to the power size, then we would move. Now along with that, I also added a and size is less than 60, because if you calculate 2 to the power this and n is very big, n is let's say 1e4, and you calculate 2 to the power 1e4, that would exceed our long range and would give us a garbage value. So we know that is very big value, but that garbage value may be negative also, that may be small value also. So it may satisfy this condition, although this thing is very big. So I know for 60, 2 to the power 60 would become somewhat 1e18. And the range of k given to us in the problem is 10 to the power 12 also. So in order to avoid this, for any, if we are taking 2 to the power greater than 60, then we can just directly say that value is greater. I'm sorry. Okay, so whenever the size is less than 60, then only we would check. Otherwise, we can say that directly it is greater. Okay, I hope that thing is clear to you. So why I put this? In order to avoid my overflow condition. After this, if this condition is satisfied, as I said, what we do is we put AR equal to I, that answer at that I would be put in the right index. So answer of R becomes I, and we call the recursive function for L comma R minus 1, and K would reduce by 2 to the power this R minus L minus 1. So L R minus 1, K reduced by 2 to the power size. Okay, and we move to I plus 1 and pass this answer array by reference. In the else part, we update our answer L and move our function from L plus 1 to R. K would remain K, and we move to I plus 1. Okay, I hope this recursion is clear to you. We have already created this recursive function. Okay, then for our answer, what we do, we already know this base condition. If K is greater than 2 to the power n minus 1, we print minus 1. So first we check the minus 1 case. Okay, so if K is greater than 2 to the power n minus 1, we print minus 1. Okay, and if again we have to take 2 to the power n minus 1. So if n minus 1 is less than 60, then only we check the condition. If it is greater than 60, we know it is greater, so it would be fine. It would be greater than K, so this condition won't be satisfied. Okay, so this condition is checked only for n minus 1 less than 60. So this way we print minus 1 and return if this is satisfied. Else we compute our answer. How we compute our answer? I create an answer vector of size n, And then in the function, I pass L from 0 to n minus 1. That is my initial size of my where I have to fill in my answer array. I starts with 1 and k starts with k. And I pass my answer vector. After this recursive function is run in order of n time, this answer vector would be updated. So I just print this answer. Okay, I've directly written cout answer because I have like overloaded my cout function uh, for vectors, but it would be better to write it like this. Okay, for auto I to answer, I cout I. Then I just cout max Wilson. Okay, I hope now it is clear. So I just print all the elements of my answer array like this. Okay, so I hope this problem is clear to you now and the code is also clear. Okay, I don't know the rating of the problem. If I have to guess, maybe 14, 1500 or 1600. Okay, maybe 1400 only. Okay, so uh, if you look at the time complexity, this recursion is in this recursion, I'm always going. Okay, I start with I as 1 and I go up till L and R become equal. Okay, and in this recursion, either I call this or this, any one is called. So every time I call the function, this distance between L and R is reduced by 1. So it's L to R minus 1, L plus 1 to R. So either I call this function or this function, the distance between L and R is reduced by 1 in the next iteration, and then again reduced by 1 and 1. When their distance become 0, or you can say L and R become equal, we return out. So at max, this function would be called in the stack at max the distance of L and R, which is from 0 to n. Okay, so at max it would be called n times. Okay, if I call this function once in order of n time, okay, in the stack at max there would be n functions that would be called in the stack. That we can see that in the if condition, either we call this function or this function, whichever we call, the distance is reduced by 1. Okay, so I hope it's clear why it's order of n. Okay, so this is called, and this answer printing would be order of n. So this function would be order of n. Answer printing would be order of n. So overall, its time complexity is going to be order of n. Okay, so is there an iterative solution? I think you can do the same thing through iterative way, that you take an L and R L while R is greater than equal to L, you run the iteration, and inside the iteration you just update your L and R and K like this only. Okay, instead of calling the function, you just update like R minus minus or L plus plus and then I plus plus and update K. So update all the variables inside the loop, and condition of loop would be R greater than equal to L. Okay, that way you can do it through an iterative code also. Okay, so it would work the same way. Okay, so I hope this problem is completely clear to everyone. If there is any more doubt, you can ask. Okay, so I think we can move to the next problem, which would be problem E. Okay, so let's discuss E. Okay, we'll not discuss D today. Okay, maybe you can look at the editorial, or if I find the logic of D, maybe I'll write in the comment. But currently, I was able to solve E and not D. Okay, so in problem E, what you have that you are given a tree with n vertices. Let's place a robot at some vertex phi which is not equal to 1. Suppose we initially have p coins. Consider the following process where the ith step starting with I equal to 1. If I is odd, the robot moves to an adjacent vertex in the direction of vertex 1. Else I is even. You can either pay 1 coin if there are some left, and then the robot moves to an adjacent vertex in the direction of vertex 1, or not pay, and then the robot moves to an adjacent vertex chosen uniformly at random. Okay, so what does this problem states that you have a robot and you have a tree. Okay, and this robot is at some vertex v, and then you have some following process. So in the ith step, I starting with 1 if I is odd. Okay, so basically alternatively, once you this process would be done, then this process, then this. Okay, in the first type of process, the robot just moves to an adjacent vertex in the direction of 1. So you can assume that 1 is the root of the tree, so the robot is moving towards its parent so that it's moving to the topmost root. Okay, that you can, like, by reading this, you can, if you know about trees, you can get this conclusion directly that moving towards vertex 1 means that if the tree is arranged like 1 is the root, then it's moving towards its parent so that it can reach 1, which is the topmost parent. Okay, now the second type of operation is you can either pay 1 coin and then the robot moves to an adjacent vertex in direction of 1. So if you pay a coin, the robot would move like the first operation only towards 1. Okay, so it would move to its parent. Or if you don't pay, then the robot moves to an adjacent vertex chosen uniformly at random. Okay, so whatever adjacent vertex are there for that vertex v, it would choose any one vertex at random and move there. Okay, so the process stops as soon as the robot reaches vertex 1. Let FVP be minimum possible expected number of steps in the process above if we spend our coins optimally. So you need to spend the coins optimally so that the expected number of steps is minimized. Okay, so FVP means that for a given vertex as the starting point, if V is the starting point in the tree and P is the number of coins available to you, what is the expected number of steps in which the robot would be able to reach 1 if we are spending the coins optimally. Okay, so I hope this problem is clear, problem statement is clear. So let's look at the first test case to understand. Okay, so here we are given this n and q. So n is 4. After that, this tree is given. These n minus 1 edges are given. Okay, so you have a tree of size 4. So you have 1, 2. Okay, you have an edge from 1 to 2. So 1 is connected to 2. From 2 to 3, you have an edge. So 2 is connected to 3. From 2 to 4, you have an edge. 2 is connected to 4. Okay, so this is the tree given to you. Okay, this is the tree given to you. And then these are the operations. These are the 4 operations that are applied. Like 4 questions that are asked basically. In every question, you need to find f of this v comma p. Okay. So here v is 2, p is 0. Okay. It means you are starting at this vertex 2. Okay. V is 2. It means you are starting here. V is here. Robot is here. And you need to reach 1. Available number of coins is 0. Okay. So 0 number of coins are available. What would happen? If you start here, first operation would be operation of first step because for I, you start with I equal to 1. 1 is odd. Okay. So first this operation would be performed. Okay, this operation would be performed. After that, this operation and then this alternatively. So first, when the robot is here, okay, it would move towards 1, okay, and it would move towards 1, and in one step, it would reach 1. Okay, so always its expected value or the actual value is also 1 only. Okay, now next case, you start with 3. Okay, you start with 3 here. Okay, so first step would be operation 1. You move towards 1. You move here. Okay, 1 is here. You know, moving towards 1 means first make this tree like 1 is the root. Okay, so that way if you make this tree, this way the tree would become and its parent would be this. Sorry. So from 3 you move to 2 in one step. Okay. Then in the next step, you do operation 2. So you don't have any coins. You cannot spend any coin. So what would happen at random? Either it would move here or here or here. Okay. So there is 1 by 3 probability that it would move here. 1 by 3 probability move here. 1 by 3 probability to move here. So if it moves here, then it reaches 1 in the next step only, and you say that 2 is your answer. So after 2 steps, it has reached here. So there is 1 by 3 probability that 2 would be your answer. Okay. Or there is probability that it would move here, or 1 by 3 probability it would move here. Then after 2 steps, when it is here, then again next step it would move back to 2. So after 4 steps, it's again back to 2. Then there's 1 by 3 probability that it moves here. So there's 1 by 3 probability for the answer to be 5. Okay. So initially there was 1 by 3 probability for the answer to be 2. Okay. Move here and here. Okay. After that, from here, if you go there, then next step would be here for sure, because it's a step 1. So after 4 steps, you are back to here. Then 1 by 3 probability to move here. Okay. So 1 by 3 probability to be 5. Okay. Then again, rest 2 by 3 probability that it goes down. Next step, it would come back here. And with 1 by 3 probability, it would go here. So again, after 8, 1 by 3 probability of 8. Likewise, it would go. So it would be 1 by 3 probability of 2 plus 5 plus 8 plus okay, and okay, sorry, it would be multiplied with 2 by 3. Okay, 1 by 3 probability was for it to be 2, and then 2 by 3 probability was to go down. So this whole thing would be multiplied with 2 by 3. Okay, and this whole thing would be multiplied with 2 by 3 two times. Okay, two times you went down. Okay, this 2 by 3 multiplied and again 2 by 3. Okay, so that would be some GP, basically that would be some GP, infinite GP, which would go down to some single value. Okay, so the value that it would go down to would be for 3 0. My answer for the second test case was 6. Okay, so it would be 6 actually, this thing. Now, how do we compute this? Okay, so like mathematically only computing this was a bit tough. But if you think a bit, then what is happening actually? Whenever you are at this position, okay, so let's consider the first step, that it goes to the parent. That step is considered. Okay, it would definitely do that. After that, from I equal to 2, if you see, every time if you don't spend a coin, you have, if you it is adjacent to C, if it is adjacent to C vertices, then there is 1 by C probability that it goes up, and C minus 1 by C probability that is goes down. And if it goes down, the next step it would again go up, because next step would be an odd step. This was an even step, next step would be odd step, definitely it would go up. Okay, so you can say that what, if it is at index V, so if with dpv you represent the, like, expected number of steps from V uh, to reach 1. In dpv, if you represent the expected number of steps to reach 1, then you can say what is the expected number of steps to reach 1. Either if it goes 1, so like C, I'm writing the number of adjacent nodes. Okay, if C is the number of so there is 1 by C possibility that it goes up. Okay, so if it goes up from here, if it goes up, okay, if it is reaching 1, then obviously in one step that would reach. But if let's say V was, let's say you have some random tree. Okay, okay, for any random tree, If you are at some V, okay, either it goes up or goes down. Okay, when it goes up, the next step he is definitely going up. So basically you can say if it is going up, that means in two steps it would reach to the parent of V. So we can say that if Y is the parent of V, okay, so whatever is V, it's parent to parent, because if it is moving up, next step it would be going up definitely. So if Y is the parent of V, then we would say that in the next two steps it would reach Y, and then whatever is the expected value from Y to reach 1, that would get added. So you can say there's 1 by C possibility. What would happen? In two steps it would reach Y, and then whatever is dp of Y, whatever is the expected number of value from Y to reach 1, that you can say. Or you can say there is C minus 1 by C possibility, that is goes down. Okay, if it is at some index V, it goes down. So there is 1 by C possibility to go up, and rest possibility of C minus 1 by C possibility, that is goes down. And if it goes down, next step it would go up and come back to V. That is for sure. Because next step is an odd step, and he would definitely go up. So in an odd step, he would definitely go up. So you can say after two steps he returns back to V. So 2 plus dpv you can say. So next step he goes down, and then next step he goes up. So in two steps he returns back to V, and whatever is expected value from V, same thing would happen. So 2 plus dpv you can write. So this thing you can say, you can take this 2 out, and you can say that it is 1 by C times dpy plus C minus 1 by C times dpv plus, okay, 1 plus C minus 1 by C, it becomes 1. So plus 2, that comes out. Okay, this thing if you add. So if dpv is this, okay, what can you say? Okay, if you rearrange this, if you take dpv here on one side, you can write dpv, this minus this is 1 minus C minus 1 by C. Okay, this would become 1 by C actually. This becomes 1 by C is equal to 1 by C times dpy plus 2. Okay, so this thing becomes dpv is equal to dpy plus 2c. Is this clear to you? Okay, so when you take this c this side, dpv becomes dp. So like from this equation, okay, we concluded that dpv would be dpy plus 2c, where y is the parent of v. Okay, that you have to remember. Whichever is V, parent to parent of that. Okay, its double parent is Y. So whatever is the expected number of whatever is the expected number of uh, uh, expected number to reach from Y to 1, that plus 2 times C would be expected value or the expected number of steps to reach from V to 1. Okay, after this, like I have written this as dp only, you can apply the dp. Okay, but this was if we don't use a coin. Okay, this was the case if we don't use the coin. What if we use the coin? Okay, you have p number of coins also. So if we use the coin, we are definitely going up. So with 100% probability, you can say dp of y only if we use the coin plus 2. Okay, so dp of y plus 2, that would be with full probability. These things will go out if we use the coin. So instead of defining the dp as just y, we would define dp as v comma p. So we'll also store the coins. Okay, p. Okay, so expected, what is dpvp? Expected number of moves to reach from v to 1 using p coins. Okay, this is my state that I'm going to take for solving the problem, and my transition would be dp of vp is actually, okay, if c is the number of adjacent nodes. Okay, so either if we use the coin or not use the coin. So minimum of both you would take, because you need to minimize that your final answer. So if we use the coin, we obviously go to dpy, like in two steps we go to dpy, and we have used the coin, so it's p minus 1. So either this would be the case if we use the coin, or if we don't use the coin, then from this you can understand it would be dpy plus 2c. Okay, you would get this case, which would finally evaluate to these things. So if we don't use the coin, it would be dpy plus 2 times c. Okay, it's not yp. We are not using the coin, it would remain, our remaining number of coin would remain p here, plus 2 times c. Okay, so this would be our state, you can say that dpp is min of this thing or this thing. Okay, where you c is the number of adjacent nodes and y is the parent of v. Okay, so I hope this transition is clear. What would be your base case? Base case would be when p become v is equal to 1, then you would say that zero number of coins are needed. Okay, when you are already at 1, you can say that no coins is, like, sorry, not the coins. When you are already at 1, no number of steps is needed. You are done with the steps. Okay, you have reached 1 already, so zero steps are needed. And when you are at the case where v is, okay, so let's say you are at this case where v is at 2, so the parent of this would be some node above 1. If that is your y, then technically writing parent of v y is invalid, because its parent of parent doesn't exist. So in this case, what you can do is, what is actually happening from 2, if you use basically from 2, if you use one uh, step. Okay, so if you are going up, then in one step only you are reaching 1 instead of 2 steps. What you are counting, that there's 1 by c probability that we go up. So if we go up, then after this we go one more step, and then in 2 steps we reach parent of y. Instead, in our final answer, in one step only we would reach 1 and we would end there. Or if we go down, then we go down and move up, and it would remain dp of 2. So that would not get affected. Only when we go up, that thing gets affected, because we are writing dp of y, which doesn't exist. So for that, what you can do is, for this your answer should have been 2, like answer should have been 1 in one step you reach here, but you are writing 2 plus dp of y. So you can take this as minus 1. Okay, so either you write a separate base case for this where your parent is 1, or what you can do is, you can assume a node as its parent. You can assume that parent of 1 is some node minus 1, and you can say that dp of this minus 1 is minus 1. Okay, you can say that dp of this is minus 1. So if we are moving here, that means you are using an extra step. So from that, if you move one step back, you reach 1. So in one step early only we have reached 1. So in my base case, what I'm writing is, if my v is not 1, so if my v is equal to minus 1, where minus 1 is the parent of 1, okay, then you return minus 1. Okay, so this thing, if I can write this as my base condition, that way there would be no problem. All this would be calculated. Even if y is minus 1, that means y is doesn't exist, it's the parent of 1, then also I am able to compute, okay, using this base case. So I hope it is clear now, and that you can look at the constraints that n was up till 2 into 10 to the power 3 only. And the number of coins p is up till n. So that is also 2e3. Okay, so this v is up till n and p is also up till n. So this dp is order of n square actually. Okay, and for computation you are just this is order of one transition. So overall time complexity would be order of n square. Okay, so I hope the approach is clear to you. Okay, this was our state, this was our transition, and this was our base case. Okay, so you can just write the base case, transition, and state and compute your DP very easily in the code. Okay, and for this what you need is number of adjacent node and the parent. Okay, so you can construct this parent array initially by running a DFS. So by running a DFS from 1, so by running a DFS from 1, you can compute this parent array, who is the parent of whom, if 1 is the root of the tree. Okay, so this parent array can be pre-computed by running a DFS, and then you can write a maybe recursive DP function or whatever you wish, through which where you would write these transitions, and you can use memoization to compute it in order of n square. I hope the approach is clear to you. Okay, so we can look at the code now. Okay, so what I'm doing here is I take the input nq. Okay, to store the tree, I'm using an adjacency list. Okay, so I assign because I have to use that in DFSN function, so I assign it global only, my adjacency variable. So in adjacency dot assign, I do n plus 1. So I have nodes from 1 to n. So I assign its size as n plus 1. So I can do it 1 based indexing. I can access n. Okay, and vector into 0. So initially 0 size. Okay, for every edge uv, I assign adjacency u dot push back v dot push back u. So I construct my tree basically. I hope you know how to construct this. After that, I have to run a DFS in order to find my parent array. So in parent array, I assign -1 initially, and in DP also, DP vector also, I assign minus. So I run a DFS with the parent of 1 as -1. Okay, in DFS, I run through x and the parent of x. So I initially assume that the parent of 1 is -1. Okay, so here I assign my parent of x as p, and I run the DFS for all the adjacency of x. Okay, so through this DFS, I compute my parent array. Okay, so once my parent array is computed, okay, then for every query for given v and p, I can write my answer as, okay, 1 plus func parent v. Okay, we'll look at, so what we can say that when we are at v, NEV, we need to compute the expected number of steps. First step would be going up. First step is of first type. Since I equal to 1 is odd. So first step you would go 1 definitely. So one step for that. And then from here, whatever is the expected value that you would add. So you would say your answer for v comma p is 1 plus func of, okay, or you can say 1 plus dp of vp. VP parent of V and P. Okay, so you'll say 1 plus func. In func, I've written the recursive DP. So func actually represents my DP of parent V comma P. Okay, so in one step, I go into the parent of V, and then if parent of V is my initial index and you have P number of coins, whatever is the expected number of steps that I'll add. That would be my answer. I print my answer. Okay, so let's look this recursive DP function func. In func, I write the recursive DP and DP of x comma p. So one thing is if p is less than 0. Okay, so like if the number of coins becomes less than 0, that's invalid. So I return infinity some large value so that that is not considered in my answer if number of remaining coins becomes negative. Okay. Now this, so this is also one of my base case, And if x is 1, return 0, x is minus 1, return minus 1. These two base cases are there. Okay, so these were the two base cases. I wrote them. Okay, then my transition is if dpxp is not, okay, I do the memoization. dpxp is not minus 1, return dpxp. So memoization is done. After that, this would be my transition. So in C, I got the number of available options would be the size of my adjacency list, number of nodes adjacent to X that I got in C, and Y is the parent of X. Okay, that is Y. So my dpxp would be, okay, I have written the transition minimum of 2 times dp yp minus 1. Okay, so like 2 plus dp yp minus 1. So dp yp minus 1 plus 2. Okay, either this or dp yp plus 2c. Okay, so dp yp plus 2c. Okay, so this way I have written my transition, and I have to do modulo m to my answer also. It's also given in the problem that I have to write print my final answer as mod this. Okay, so in m we take that value, like you can, so in m I take that value and I do a mod m there after calculating the dp this mod m plus m mod m, because the value of dp can also be minus 1. So I also do plus m mod m in order to ensure that my, after doing mod m, my value is positive. Okay, if it is negative, then modem would keep it negative only. So plus m modem would make it positive. So that way, and then I return dpxp. Okay, so I hope this recursive dp function is clear. So that way I just compute my answer for every query. Okay, and what would be its time complexity? That, okay, so I'm using memoization here. So memoization is used. So this function would be computed at max, and this dp times the size of the dp is n into n. Okay, so this function would be run at max n into n times. Okay, after that, this memoization would return in order of 1 only. So due to memoization, its complexity would be n square. For every query I am running this. Okay, so this function overall for all queries combined would run at max n square times only, and these are order of 1. Okay, so this is run q times. So my final time complexity would be order of n square plus q, you can say. Okay, for every query you are running q times. So this would be my time complexity. I hope this problem is clear to you. Is there any more doubt? What's the significance of 1 plus f? As I explained here, that my dp, what my dp state is, expected number of moves to reach v to 1 using p coins. But here the number of moves, I'm starting with the second type of move. Okay, here I'm assuming the next move is the second type of move, this move for even I. Okay, but in the problem, I start with the first type of move. So I perform this first type of move and then write the DP, because in my DP, I'm assuming the current move is second type of move. Then only if I'm using the coin or I'm taking the two cases. Okay, in DP, I'm taking the two cases that if I use the coin, I write this. If I don't use the coin, I write this. So that would only happen if the currently I'm doing the second type. Okay, second type of operation is performed. So but in the question I'm starting with first type. So in order to convert this, what I did, the first type operation is performed, one move is done, after that I call the function. Okay, okay, so any more doubt to anyone? Okay, dry run for test case, I think doing a dry run for DP would be little, but okay, I'll do it for this. If you wish to compute, then like I told, if you want to compute for like this 3 comma 0, okay, that means you are here, you write your answer as 1 plus dp of the parent of this is 2, and with zero number of coins available. Okay, or if you compute for with one coin. Okay, so let's say I'm computing for this. Okay, not this. Okay, so its answer would be 1 plus dp of parent of 3, which is 2, and one coin available. Now, how you compute dp of 2, 1? dp of 2, 1 would be, what is parent of 2? It is minus 1. Okay, so here your y would be minus 1, and number of adjacent nodes is 1, 2, 3. C would be 3. Okay, so here you would write it as min of either deep. So if you use the coin, then you reach y in 2 steps, and if you don't reuse the coin, then you reach y in 2c steps. Why is it 2c? That we already proved through here. Okay, so in this we already proved that. Okay, so you reach y in 2c steps. Okay, min of this. So y is minus 1 here. So this would be min of y is minus 1 plus 2 is 1. Minus 1 plus 2c is 2 into 3, 6. So 5. Okay, min of that would be 1. So this would return me 1. So 1 plus 1 would be 2 for 3, 1 case. For 3, 1 case, my answer was 2 here. Okay, and for even for 3, 0 case, okay, even for 3, 0 case, you can see that if number of coins was 0 here, that means this operation we cannot perform. Here my number of coins would become minus 1, so this would return me infinity. So only this thing would be considered, and this is 5. So we would get 1 plus 5 here. So 1 plus 5 would be 6. Okay. So for this third case of 3, 0, we are getting 6. Okay. I hope it is clear to you now. Okay. So is there any more doubts in this problem? Okay. Uh, I think this was easier than the D problem, maybe, or I was missing something in D. But for E problem, I didn't feel that this was like an E problem. So, okay, I think if this problem is clear, then we can exit. Okay, so thank you very much for tuning in, guys. Goodbye.